In this video we'll be looking at the final challenge in the ROP Emporium series, so it's called ret2csu, and it says we're back in the ret2win territory, but this time there's no useful gadgets. How will we populate critical registers without them? And you'll see there's no 32-bit edition for this, so we're just going to focus on the 64-bit. And it says the challenge is the same as the call me challenge, so there's a pwnme function along with printing. The pwndbg function along with the printing logic has been moved into a library to mitigate alternative solutions that be available. Our goal is to simply call ret2win and pass in these accompanying functions. For us it'll be these ones because they're using 64-bit. And it's just explaining here that the problem we're going to face here is populating the elusive third register using ROP. And some more information about that here. Start by using ropper to search for sensible gadgets. If there's no pop RDX, perhaps you can move RBP to the RDX and then pop and chain that with a pop RBP. If you're out of ideas, go to the last section. And the last section is going to refer us to this paper on the ret2csu technique, which was presented at Black Hat Asia. So we'll take a look at that shortly. Let's first of all just go and do some initial checks on the binary. So let's open this up in pwndbg. Ret2csu, and let's disassemble, see what we have here. We have a useful function. We don't have the useful gadgets or questionable gadgets or anything like that in here. Let's disassemble our useful function. Okay, so in here we have some move instructions: move RSP to the RBP, move 3 to EDX, 2 to ESI, 1 to EDI, and then call ret2win. Okay, let's generate our cyclic pattern of 100. Run the program. It asks us for an input. Paste it in, and we check the offset to the bytes. Cyclic -L, and our offset is 40. Okay, let's close that down and let's just open up. Let's open up the library quickly, ret2csu, and see what we have in here. If we go to disassemble, so this is where our pwndbg function is. It's been moved here to bypass an alternative solution or alternative solutions, but I don't see anything else in here in terms of questionable gadgets or anything like that. So let's go and take a look with ropper and see what we can find. Okay, let's search. Let's do ropper-f and ret2csu. Let's list all the gadgets here first, and let's check specifically for pop. So, oops, --search to search for that. What I'll also do here is just open up our call me code, the 64-bit, just to see roughly what we did here previously. So previously okay, this was to 3 separate functions, but essentially what we're looking to do here is just call one function, ret2win, and we want to pass these same parameters in. You see, what we did here is we did the pop3. We popped the first value to the RDI, the second value to the RSI, and the third to the RDX, and that places the parameters into the required registers before the call me function was made. So let's go back to ropper. Just keep this open for the time being, and we have do we have pop RDI? We have a pop RDI here. We need a pop RSI. We have a pop RSI in R15, but we don't have the pop RDX. So a potential solution that was suggested for us was maybe we could move RBP to RDX. Let's see if we have a move instruction. Move, and let's grep RBX. No. Sorry, RDX. No. Yeah. Okay, so it looks like we'll need to look into another solution. Let's also just quickly check the library, the lib library. So we have some more in here. If we can search for pop. Okay, we have a pop RBP. So if we had a move RBP to RDX here, which we don't in this case. So we need to look into the solution that was suggested to us. So this technique, universal ROP, or return to CSU here. So if we open up the Black Hat Asia paper where this is described, this is a good paper worth taking a look through. Essentially what it's describing here is that the CSU library is attached whenever a binary is dynamically compiled. So if you just create here's a minimal program, doesn't do anything, but it attaches this CSU library. You see here libcsu, and the authors basically describe how they've been able to chain some ROP gadgets together that are present in all of those, in all binaries compiled with that library, which is like 98 or 99% of binaries. Sorry. They also describe how the ropper and ROP shell wasn't able to build up the ROP chains, even though the gadgets were clearly available in the code. I think it found the individual gadgets but wasn't able to chain them together. And then they actually analyzed the code in question. So you have here the libcsu init function, and you can see here they've separated out two gadgets. Essentially what they're explaining here is that if we want to get our values into the RDX, RSI, and RDI ready for a parameter call, we can first use this gadget 1, which is available in the libcsu, and this is going to pop. First you have this pop RBX and RBP, and then you're going to pop to R12, R13, R14, R15. So if we can pop the values to these registers, we can then move them to the required RDX, RSI, and RDI for the placed in the correct way that parameters need to be on the 64-bit. So I'm just trying to think, is there anything else I really need to cover in here? There's quite a lot of information, including some countermeasures. So I would take a read through this. Essentially, we've got what we need to get from here. We know that these are the two gadgets in question, and that this is gadget 1, which is going to allow us to get our variables into the R12 to R15 registers, and then this gadget 2 is going to allow us to move those into the required parameters before using this call. So let's go and see if we can put this together. Let's minimize this in case we need to go back to it. Okay, so let's check with ropper here now that we've had a look at that. Check with the file, ret2csu, and see if we have a pop RSP R13. We need the pop RBX all the way to R15. Here's a pop RBP to R15. So that's everything but missing the RBX. So we can try and search pop, and you see here we have this full one, we don't have the pop RBX in front of it, but if we take a look at this address, let's see if we can copy that and gdb pwndbg ret2csu, and let's disassemble at that address. Okay, 0x. Okay, and if we disassemble at that address, 69B is right here. So we have the pop RBP, R12, R13, R14, R15. We actually have a pop RBX right before it. So we do have the full gadget there, but ropper was only showing us from this point onwards. I'm not too sure. There might be a way to search for longer gadgets in ROPER, because I do notice that in this paper, which was Asia 2018, that you know, they submitted a fix for ROPER, I think, or suggested a fix. So I'm probably doing something wrong there. But anyway, we've got our gadget number 1. Now we need gadget number 2, which is move. So let's have a look in ROPER this time. Have a look at the move, and we're looking to move RDX, RSI, EDI. Okay, so no sign of it there. Let's go back here, see what we can disassemble. And if we try to disassemble libcsu init, which I believe was the function that they were disassembling here, looking for the gadgets. So here you had a move, which is gadget 1. Okay, so we have our pop gadget here at the end, that's our gadget 1. And then we have our move gadget here as well. So move R15 into the RDX, move R14 into the RSI, R13 into the RDI or EDI. And then it makes this call. So we have our 2 gadgets. We would take these 2 addresses here, take the 680 and take the 9A. I've already done that, so let's go ahead and open pwntools debug. Let's just do a quick comparison here and see what we have. Oops. Okay, 1 second. GDB pwndbg file ret2csu disassemble, and it was the libcsu init. Disassemble that. So the first gadget was 69A. You can see here we have our gadget defined 69A. That's our full pop RBX, RBP, R12, etc. And then we have our CSU move, which is a 680, and 680 is our CSU move. Okay, so just to show that that's where we've identified those addresses. And let's have a dig through the code now. I mentioned before we go through the code as well that I've left some links at the top of the script to some other write-ups and information which helped me throughout this. So you'll see there were some places I got stuck with the exploit and I referred to these, which I'll try to mention as we go through it. But we also have our pop RDI and then our return to win address, which obviously is where we need is the function we need to call at the end. We print out all of these gadgets and the addresses and things like that, and then we go to start building our payload. So I'm going to describe the payload first, and then I'll go through debugging it a little bit and try to show what's happening step by step. So we in this case we found our offset, which will be 40, and we're doing 40 bytes of NOPs, and then we call our pop operation. Now we want to fill the RDI, the RSI, and the RDX, and we have our move gadgets, which is going to move R15 to the RDX, R14 to RSI, and R13 to the RDI. So we first have these 3 pops. We have a pop RBX, pop RBP, and pop R12. So I've put there fill with junk. It's not junk. I'll try to explain what we have there and why, possibly with some help from one of those write-ups I mentioned. But let's not worry about these 3 yet. We're popping the dead beef into the R13, cafe babe into R14, and dude food into R15. Then we call our move operation, and move is going to move that R15 into the RDX, it's going to move that R14 into the RSI, and it's going to move this R13 into the EDI. Now note that do I still have the ROPER open here? Okay, so we have this R13D and it's going into the EDI. So that's only basically going to take a 32-bit address. So it's only going to take the dead beef. It's not going to take the full thing. So we'll need to deal with that later. As you can see, I've done here. I'll show that when we're debugging. So it does a move operation, and then there are 6. Whenever it makes this call, there are going to be 6 pops which will occur, which we need to get rid of. So we have this just to pop zeros into those registers, and then we get to the stage where we need to pop RDI again, just because we didn't get the full dead beef in there. We pop that into the RDI, and then we call our return to win function. Okay, so hopefully I explained that okay. It will maybe look a bit better when we try to visualize it here with GDB. So let me uncomment the GDB attach, and this is going to create the payload, and then we're just going to set these breakpoints. So I have a breakpoint set to our pop here. I have a breakpoint set to the CSU move right here, and then we have a breakpoint set to return to win as well. And we'll step through each instruction. So with that saved, let's go and try and run this. Okay, so we run Python pwntools debug. We get our GDB window here. You can see it's set up our breakpoints for us and started pwndbg. Let's go next, just go to the next instruction. You can see everything's lined up here. Let's take a look and see what we've got at the RSP. So we can do x over, let's say, 50x, and then pass in the RSP. You can see here then we've got our stack lined up. We have our no operation instructions, 40 bytes, leading up to our, let's compare this to what we have in the code. So we have our ASM NOPs going right up to 0 here. So we have this 03 for the RBX, so there's our 3. We have the 04 for the RBP, there we go. We have this address input to go to the R12, and then we have our parameters that are going into the R13, dead beef, cafe babe going into RSI, and then finally dude food going into the into the R14 and R15. They'll be moved after that. And then we have the address of the CSU move, so that's 680. You can see that right here. We have all of our 0 bytes because we're going to be popping. It's going to be running through some pop instructions in the background, and we don't want it to use up our calls to return to win and popping dead beef on the stack. So it's going to go through all that. Finally, it's going to pop RDI, so that's the A3 value that we have here, and it's going to pop the dead beef into the RDI, and then finally call return to win. You can see here is the 40. So everything, looking at the stack, it looks like we've lined up everything as we would like it. Let's see if we can go through now and step through the instructions. So let's just hit N for next instruction, and okay, you can see this starting to line up here. So we have our pop RBX, pop RBP, pop R12 all coming up. That's next instruction, next, and here we're returning to 69A. So 69A is our pop instruction. So hit next. Hit it twice, and we're popping RBX. So the value that's currently on the stack. Let's have a look at our stack again. We're going to pop this 3 to the RBX, so let's hit next, and then our RBX is now 3. Then if we wanted to do, let's do, can I just do print RSP? Okay, we'll just do X RSP. RSP we have there is now 4, and then we have a pop RBP, so we'll hit next instruction, and then our RBP is now 4, so we've got 3 and 4 in there. We're now going to pop our this memory address to R12. Let's do that. We're going to pop our, let's check the RSP. RSP is containing dead beef, so we're going to pop dead beef to the R13 next, and you'll see R13 now has dead beef in it. Next, we're going to pop Cafe Babe. You can see here in the RSP, we're going to be popping that into the R14. So next instruction, you can see R14 is now populated, and then finally we'll pop our final one, which is the dude food, into the R15. So let's go next again, and there you go. You can see we've populated all three of those. And then this is returning to this address. So let me, before we continue with that, let me go and open up one of these write-ups. Open. So if you take a look through one of these write-ups, it'll explain a little bit more about what's happening with, let me just show the, so the address that's been identified there has been, yeah, they have a similar address to me. It's essentially a place has been picked to that will return back to the CSU. You see this lib CSU in it. So they've essentially just found an address which is going to go through a few instructions, and then it's going to return back to the lib CSU right after the call. So I did try that with some different variables in there. The code that I actually used initially, let me open this as well, give some credit to the original authors. This is a code I was looking at originally where they'd use this address here. They also assigned 3 and 4 for the compare, and I looked at this one just because there was a better explanation of what was going on. It was a little bit different in that in this example they use a 0 and a 1 in the RBX. You see here 0 and 1, whereas we're using 3 and 4. I did try it with 0 and 1, and I'll actually demonstrate in a minute what happens, the difference. I don't know whether maybe the difference between that, I noticed that they note on the exercise here that recent versions of GCC may use different registers from the example, including the version that compiled this challenge, so there may be some variations there, or this might be referring to the old ret2csu challenge because they were all updated there in the summer. But I just thought I would just explain what's going on there. We could go and have a look at the address. Let's actually, the address that's going to be jumped to is this address. So let's see if we can, this 680. Okay, let me copy this. Let me go back to pwndbg here and let's disassemble. Okay, what was the address? E30. Okay, so you have the E30 here, and this is, it doesn't actually show the return there, but this is where we're jumping to here until it goes to a return. Yeah, I'm not sure if it's running through all of that. Let's go back to the debugger and see if we can trace it through. So we'll go next instruction, and that was the move operation that was being called there, by the way, the ending 680 that we just saw. The move operation, so that's now got our move RDX, R15 to RDX, R14 to RSI. So these are the, we've now got our dead beef in R13, our Cafe Babe in R14, etc. And that's what we're doing here. So let's do the first one. We want to move this R15 to our RDX, which currently has 0 in it. So next instruction, we do that. You can see the RDX now has the value we want, and we're going to do the R14. So we're going to do Cafe Babe into the RSI, which is here. So let's next instruction, and you can see we've done that, no problem. This is the issue here, is the dude food one. So not dude food, sorry, this will be our dead beef, you can see here that rather than using an RDI, it actually has EDI, so it's only going to do half the value. Let's hit next, see what it looks like. You can see there it's only sent dead beef instead of dead beef. and it's only populated that with dead beef, which is why we need to pop this onto into the RDI again at the end. Okay, and the next instruction then is this comparison. So this seems to be where if I set these to 0 and 1 instead of 3 and 4, it will cut out at this part. I guess the RBX value here maybe needs to be 3 because it's doing this 3 times. I guess I'm not exactly sure. If somebody has got a good explanation, please refer me down below. I'd be interested to know. But after that, what we're going to also have is we're going to have this add 1 to RBX, and then we're going to have this compare RBX to RBP. And if this returns 0, then we're going to continue with our execution basically. So that's why we have this set to 3, and we have RBX, RBP set to 4, because it's going to hit this instruction. It's going to add 1 to the RBX, and then they're both going to be 4, and then the comparison is going to hold true. So let's hit the next instruction. You see it got through that, no problem, got through the call. It's now adding 1 to the RBX, adds 1 to RBX, now RBX and RBP both equal 4, and then it does the comparison and is able to continue. So if we go back to our code, we have so these are the instructions which are occurring afterwards, and you can see that we have our 0 values. So pop RBP, let's have a look at our, you can see the value on the stack is a 0, but let's do x over 20x RSP. So you can see we have all our zeros here, and it's just for these pop instructions. So it's going back through this pop RBX, pop RBP, pop R12, etc. Popping 0 into each one of those. We could go through and hit next each time. We'll see each one of those slowly become 0 until the R15. You see one by one, all become 0. R15 is about to be 0. See, R15 is now 0, and then it went through the return. Now we are going to pop RDI, which is 4006A3, and you can see that here in the RSP. So let's hit next again, and we have dead beef in the RSP, and the instruction is pop RDI. So it's going to pop this value into the RDI up here, and that's going to give us a full address there. So next, and there you go. You can see we've lined up all the registers that we need. So then the next instruction is going to be to jump to return to win, and return to win is going to grab those parameters. So let's just continue. Let's close everything down. Let's just try and you can see it printed out the flag there. Let's try and run that without that in there, and you can see we get our flag. I hope I've explained that okay. It was probably a little bit long, and I'd say the some of these write-ups might explain it a bit better. It's kind of it's kind of hard to do on the fly, you know. But one thing I could do is go back and demonstrate this, the 0 and the 1. If we change this to 0 and 1 and run that, you see we don't get our flag. If we set this to break again and skip through, let's hit continue to the next breakpoint, and we have our pops occurring here. We'll go through each one of these pops, and then we return. This is go into our move instruction. We do our moves, move, 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 and then it's when we get to this call. So there's this because we don't have the RBX set to 3. I guess it's what causes this to. You see, we get our invalid address 0xc. So 0xc. So yeah, that's why we've assigned those as 3 and 4. Again, this I'll update the comment on this. This isn't junk. It's to ensure that our execution jumps back to the libcsu init after it's finished. Okay, and finally then we'll look at the AutoPwn script and see how much of this we can automate. I'm not too, because we're using like kind of custom ROP gadgets here, I'm not too sure that we'll be able to do too much, but let's take a look. So open up the AutoPwn script. We're just manually putting in the offset this time, just trying to keep the script as short as possible. So what I was trying to do here, which would have been really nice if it worked, would be to simply call ROP call ret2in with the parameters. Our parameters here we've just got as an array. We're using this ROP object so that we can find gadgets and stuff here. But I was hoping that this would work. Let's see what happens when we try and run it. Python AutoPwn. And you get here, could not satisfy set registers. So it tried to set the 3 registers with our parameters, and it wasn't able to set them, which is the same issue that we obviously have, in that we need to use this ret2csu technique. But I'm a little surprised that, you know, since that paper was released, this kind of functionality hasn't been put into pwntools, and we seem to have some problems with ropper earlier as well, finding the full gadgets and stuff like that, unless that's just me. But let's uncomment this. Unfortunately, it's not too much better than our previous script. It's pretty much the same in terms of the actual payload, but we're using the ROP object, rop.raw, to convert this all into to basically pack them into a ROP chain different, so you can put in here integers, strings, things like that. This is where we're going to convert into the raw bytes, the ROP.chain. So we do our pop in just as before, pop 3 and 4 into our RBP and RBX and RBP. We have this address pointing to the .fini section so that it will return to the ret2csu init after if it jumps this address, it'll execute for a little while, and then it'll return back to where we need it to go, basically. And then we have our parameters here, which are going to be popped, which are being put in place for this move from R13 to R15. So you can see here we're popping, just as before, we're popping these into R13, R14, R15. Then we call the CSU move, and we had those the series of pops that we need to deal with, so we just pop 0 into each of those registers. And then finally, because our gadget here only put half of our dead beef address into the RDI, we need to pop to RDI again and just send this first parameter in again. And then rather than putting in the address manually of the return to win, we've just allowed it to find it through the function. So we do that, and then we create a payload which is just saying at the padding offset, which is 40, insert this ROP chain. So let's save that, let's run the application. You see we print out our ROP chain here, and it sends it off and it gets the flag. So we also save that to a payload, so we can cat out the payload. You see that there, nice and short. And we can also run the application, so ret2csu, and pass in the payload. And there we get our flag. Okay, I hope you've enjoyed the final video in the ROP Emporium series. I think this was probably the worst in terms of me explaining it, but I hope you've learnt something from it anyway. And any questions, comments, leave them down below. Thanks.